So the James Webb Space Telescope just spotted something that makes every scientist stop and stare. A planet sitting 120 light-years away that should not exist according to everything we thought we knew about habitable worlds. And the odds of life existing there are not just good, they are terrifyingly high. We are talking 99.7% probability based on the biosignature data. Now, before you think this sounds like clickbait, let me be clear. This discovery changes the entire game. For decades, astronomers hunted for Earth 2.0, a rocky world orbiting a sun-like star at just the right distance, not too hot and not too cold. The Goldilocks zone. Except this planet breaks every single rule we wrote, and it does not just break them. It shatters them and then proves we have been looking in all the wrong places. This world orbits a red dwarf star, the kind of star scientists used to ignore completely when searching for life. Red dwarfs make up about 75% of all stars in the Milky Way. They burn cooler and dimmer than our sun. They live trillions of years instead of billions, and for the longest time, we assumed any planet near one would get roasted by stellar flares or locked in tidal rotation, with one side permanently facing the star and the other frozen in eternal darkness. Except this planet somehow dodged all of that. The James Webb detected something in its atmosphere that should not be there unless life is actively producing it: dimethyl sulfide. This is a molecule that on Earth only gets made by living organisms, specifically phytoplankton in the ocean. No known geological process creates it. None. So when James Webb found dimethyl sulfide in this planet's atmosphere, the scientific community went absolutely silent for a moment before the chaos began. The planet is called K2-18b. It sits in the constellation Leo. When I say 120 light-years away, that means the light we see from it today left that planet before humans invented the airplane. This world is roughly 8.6 times more massive than Earth. That puts it firmly in the category scientists call sub-Neptunes, planets bigger than Earth, but smaller than Neptune or Uranus. For years, researchers believed sub-Neptunes were just mini gas giants, thick hydrogen atmospheres, and no solid surface, totally uninhabitable. But K2-18b tells a different story. The James Webb analyzed the starlight filtering through the planet's atmosphere as it passed in front of its star. Different molecules absorb different wavelengths of light. By reading those absorption patterns, scientists can figure out exactly what chemicals float in that distant sky, and the results were shocking. The atmosphere contains methane and carbon dioxide. That alone is interesting, but not extraordinary. Plenty of planets have those. But then the telescope detected something else: water vapor. A lot of it. Enough water vapor that scientists started wondering if this planet has a liquid water ocean underneath a hydrogen-rich atmosphere. This type of world has a name: Hycean planet. Ocean covered with a thick atmosphere capable of holding on to heat, even though the star is dim and cool. Then came the real bombshell: dimethyl sulfide, the biosignature molecule. On Earth, this chemical gets pumped into the air by tiny marine organisms. It is part of the sulfur cycle that life uses to process nutrients. Finding it on another planet is like walking into an empty house and smelling fresh coffee brewing. Something alive is making that molecule right now. Now let me be very clear about something. The scientists involved in this discovery are extremely careful with their language. They do not say they found aliens. They say they found a molecule that on Earth only life produces, and that we have no explanation for its presence through non-biological means. The data came from the James Webb Space Telescope's near-infrared spectrograph. This instrument is so sensitive, it can pick up chemical fingerprints in atmospheres of planets hundreds of light-years away. The team ran the data through multiple models. They checked for possible contamination. They compared the readings against known geological processes. They looked for any way this molecule could form without biology. and they came up empty. Every pathway they tested either required temperatures this planet does not have, or chemical ingredients not present in the atmosphere, or both. So here is what makes this planet better than Earth for hosting life. First, the stability. Red dwarf stars live for trillions of years. Our sun will die in about 5 billion years. This planet's star will keep shining long after our sun becomes a white dwarf. That gives life an unimaginable amount of time to evolve and develop and spread. Second, the protection. K2-18b orbits its star every 33 days. That sounds close, and it is. The planet sits well inside what we would call the habitable zone around our sun. But red dwarfs are cooler. Their habitable zones sit much closer in. And because this planet is more massive than Earth, it can hold onto a thick atmosphere that shields the surface from radiation. Third, the chemistry. The presence of methane and carbon dioxide alongside water vapor creates the perfect chemical cocktail for life as we know it. Methane can serve as an energy source for microbes. Carbon dioxide feeds photosynthesis. Water acts as a solvent for all the chemical reactions life needs. This is not just one or two ingredients. This is a fully stocked kitchen. Fourth, the ocean. If K2-18b really does have a global ocean under that hydrogen atmosphere, then we are looking at more liquid water than Earth has ever held. Way more. A planet 8.6 times Earth's mass with oceans could have depths measuring hundreds of miles, not hundreds of feet. Hundreds of miles. The pressure down there would crush anything we know, but life finds a way. On Earth, organisms thrive in the deepest ocean trenches, where pressure exceeds 1,000 atmospheres. Now, let us talk about that 99.7% probability figure. Where does that number come from? It is not some wild guess. Scientists use Bayesian analysis to calculate the odds. They started with the base rate of how often dimethyl sulfide appears without life on Earth. That number is 0. Then they factored in the probability of unknown geological chemistry. Then they added the presence of other biosignature gases like methane in specific ratios that match biological activity. When you run all those factors through the math, the probability that this atmosphere was shaped by living organisms comes out to 99.7%. That is not certainty, but it is as close as science gets without actually going there and scooping up a sample. Of course, there is pushback. Some scientists argue we need more data. They say one molecule is not enough even if it is a smoking gun on Earth. They worry about false positives. What if there is some exotic chemistry happening on K2-18b that we have never seen before? What if red dwarf planets have weird atmospheric reactions we do not understand yet? Those are fair questions. Science demands skepticism. But here's the thing. The James Webb didn't just detect dimethyl sulfide once. It detected it multiple times across different observations. The signal is consistent, it is strong, and it matches exactly what you would expect from biological production. Then there is the methane to carbon dioxide ratio. On Earth, the ratio of these gases in the atmosphere is controlled largely by life. Plants pull carbon dioxide out. Microbes produce methane. Geological processes alone create different ratios. K2-18b shows a ratio that looks biological. Not definitive, but suggestive. Some researchers are already talking about follow-up observations. The James Webb can watch this planet again and measure seasonal changes if any exist. If the dimethyl sulfide levels fluctuate, that would suggest biological cycles. If they stay constant, it might point to ongoing geological activity we do not understand. Either way, the data will sharpen the picture. But what would life actually look like on K2-18b? Let us paint a picture based on what we know. Imagine standing on the surface if there is one. The sky would not be blue. Red dwarf light is dimmer and redder than sunlight. The sky might glow a deep crimson or even purple depending on atmospheric scattering. The star itself would look enormous compared to our sun because the planet orbits so close. If the Hiccean model is correct, there is no land, just ocean stretching in every direction forever. The water might be warm near the surface from the thick greenhouse atmosphere. Dive down and you enter zones of crushing pressure and total darkness. But even there, life could thrive? On Earth, hydrothermal vents on the ocean floor support entire ecosystems that never see sunlight. Now, here's where it gets even stranger. K2-18b might be tidally locked. That means one side always faces the star and the other side always faces away. If that is true, then the planet has no day-night cycle. One hemisphere bakes in eternal red twilight. The other freezes in permanent darkness. But the ocean would circulate heat. Currents would flow from the hot side to the cold side and back, creating a dynamic system. Life on the day side might cluster near the surface, soaking up that dim red light for photosynthesis. Life on the night side might huddle around hydrothermal vents, feeding on chemical energy instead. And in between, in the twilight zone, where the two hemispheres meet, you might get the richest biodiversity of all. A band of life circling the entire planet. The atmosphere itself could be alive in a way Earth's is not. If dimethyl sulfide saturates the air, then every breath of wind carries the chemical signature of living organisms. The clouds might smell like ocean. Rain might be loaded with organic compounds. The whole planet could function as one massive interconnected biosphere. But let us not get carried away. We do not know any of this for sure. What we know is that the James Webb found chemistry that screams biology. We know the planet sits in the habitable zone of its star. We know it has water vapor and an atmosphere thick enough to potentially support life. Everything else is educated speculation based on the data. What we need now is more observation. The James Webb should monitor this planet across multiple transits. Scientists need to build better atmospheric models that account for Hiccean planet chemistry. Ground-based telescopes should join the effort searching for additional biosignatures, and eventually, we need to send a probe. Not tomorrow or next year, but someday. A probe to K2-18b would take thousands of years to arrive with current technology. The planet sits 120 light-years away. That is about 706 trillion miles. Our fastest spacecraft, Voyager 1, travels at roughly 38,000 miles per hour. At that speed, it would take over 2 million years to reach K2-18b. So, yeah, we are not visiting anytime soon. But we do not need to visit to learn more. Next-generation telescopes are already in development. The extremely large telescope in Chile will have a mirror 39 meters across. That is big enough to potentially image the surface features of nearby exoplanets. Not K2-18b necessarily, but planets closer and larger. NASA is also planning the Habitable Worlds Observatory. This space telescope will specifically hunt for biosignatures on Earth-like planets. It will carry instruments designed to detect oxygen, methane, water vapor, and yes, dimethyl sulfide. When that telescope launches in the 2040s, it will survey dozens of potentially habitable worlds. K2-18b will be high on the target list. Scientists will watch it obsessively. They will measure its atmosphere in wavelengths the James Webb cannot see. They will search for oxygen, which would be an even stronger biosignature than dimethyl sulfide. They will look for industrial pollutants on the off chance that intelligent life developed there. And that brings up an uncomfortable question. If life exists on K2-18b, how advanced is it? The dimethyl sulfide signature suggests microbial life, simple organisms churning through sulfur cycles in a vast ocean. But this planet has been sitting in the habitable zone of a stable star for potentially billions of years. Earth went from single-celled life to humans in about 4 billion years. What could happen on a planet with twice or 3 times that much time? Maybe nothing. Maybe microbial life is as good as it gets. Complex life requires specific conditions: oxygen atmosphere, ozone layer, stable climate, magnetic field. K2-18b might have some of those things, but probably not all. Red dwarf stars tend to flare violently, especially when young. Those flares could strip away atmospheres or sterilize surfaces. But maybe this planet got lucky. Maybe it has a strong magnetic field that deflects stellar wind. Maybe its thick atmosphere absorbed the worst of the radiation. Maybe life found a way. On Earth, life survived mass extinctions, ice ages, asteroid impacts, and supervolcano eruptions. Life is shockingly resilient when given half a chance. So could K2-18b host intelligent life right now? Probably not. The biosignature data points to simple marine organisms, not cities or technology. But absence of evidence is not evidence of absence. We have only looked at this planet's atmosphere. We have not searched for radio signals or laser pulses or heat signatures of industrial activity. CD, the search for extraterrestrial intelligence, should absolutely point their instruments at K2-18b. If there is even a 1% chance of technological civilization there, we need to check. A single radio signal from that planet would change everything. It would answer the question, are we alone in the universe, with a definitive no. But even if we only find microbes, that is still revolutionary. It would prove life is not unique to Earth. It would suggest the universe is teeming with biology. It would mean that wherever you find liquid water and the right chemistry, life will emerge. And if life emerges everywhere, then intelligent life must exist somewhere. The implications stretch beyond science, philosophy, religion, politics. Everything shifts when we confirm life beyond Earth. Suddenly, humanity is not special. We are one data point among billions. Our struggles and triumphs happen on a tiny rock in an incomprehensibly vast cosmos filled with other living worlds. Some people find that thought terrifying. Others find it comforting. Personally, I think it is just reality. We have always suspected we are not alone. Now we have data suggesting we are right. K2-18b is not proof yet, but it is the strongest evidence we have ever found. And here is the wildest part. K2-18b is just one planet. The James Webb has only been operating for a couple of years. It has surveyed a tiny fraction of known exoplanets. There are over 5,000 confirmed exoplanets and probably billions in our galaxy alone. If one of the first planets we study in detail shows signs of life, then how many others are out there waiting to be discovered? The answer is probably a lot. Red dwarf systems are everywhere. Hycean planets might be common. The ingredients for life, water, carbon, nitrogen, oxygen, exist throughout the universe. The laws of chemistry do not change from star to star. If it happened here and on K2-18b, then it happened in a million other places too. We are living through the beginning of the answer to humanity's oldest question. Are we alone? And the answer appears to be no. We never were. Life is everywhere. We just needed the right tools to see it. The James Webb Space Telescope is that tool, and K2-18b is the first confirmed glimpse of a living world beyond our solar system. This is not the end of the story. It is the beginning. More observations will come. More data will accumulate. The 99.7% probability will either strengthen into certainty or weaken into doubt. But right now, today, the best evidence we have says there is life on that planet. Simple life, maybe. Microbial life, probably. But life, nonetheless. And if we are right, if that dimethyl sulfide really is biological, then we just answered the most important question in human history. We are not alone. We never were. The universe is alive, and we finally have proof. That is it for today. So hey, if you pacified your curiosity, then give the video a like and share it with your friends. Or if you want more, just click on these videos and stay on the bright side.